Hey everyone, welcome back. Today we want to talk about the L'Hopital troll. So let's look at the following problem. It's a classic. I love to show my Calc 1 classes this. So this is the limit as x approaches infinity of the square root of x squared plus 1 over x. And the first thing I want to do is, of course, check the form. So if I'm going to use L'Hopital's rule, I want to make sure that this is in an appropriate form. And so, yeah, step one, let's go ahead and check the form. So let's see what happens to the numerator. So as x gets large, this is monotonically increasing. So this will blow up to infinity. And for the denominator, as x gets large, this is monotonically increasing and, well, unbounded, right? So as x gets big, this will get big. This will go to infinity. So that's in one of the appropriate L'Hopital's form. So notice that I write the form on the side. I don't say that this is equal to infinity over infinity. It's certainly not, but that's the form that it's in. And so I'm going to just check this. So this is in an appropriate L'Hopital's form. So I'm going to say this is equal to, by L'Hopital's rule, the limit of the derivative of the numerator. So that'll be, so be careful of the chain rule, of course. This is 1/2 quantity x squared plus 1 to the minus 1/2 times by the chain rule 2x. And this is all over the derivative of the denominator, which of course is 1. So I want to clean this up algebraically. So what do we have here? We have the limit as x approaches infinity. Of course, the 2's are going to cancel. And I have x times, well, this, but this has a negative exponent. So it's going to get set to the denominator as a, well, square root. So denominator, square root, x will stay, 2's will cancel. And this seems kind of curious, right? So let's see, are we, maybe we're a bit closer to where we need to go. So of course, now that this is cleaned up, I want to check the form. And so as x gets large, this is increasing and unbounded, so this will go to infinity. And for the same reasons, as x gets large, this will go to infinity. So I have another infinity over infinity form. That means I'm allowed to use L'Hopital's rule. And so let's see what happens here. So by L'Hopital's rule, we have the following. So we have the limit as x approaches infinity of the square root of the numerator. Not the square root, the derivative of the numerator. Yikes on that one, right? So the derivative of the numerator over the derivative of the denominator. So of course, when I take the derivative of the denominator, I want to be careful, right? Look out for chain rule. So that's going to be 1/2 x squared plus 1 to the minus 1/2 times 2x by the chain rule. Okay, so my next goal is to clean this up algebraically. And we're going to notice that the 2's are going to cancel. The x is going to stay put because it has a positive exponent. And this is going to get sent right here to the numerator as a square root. So numerator square root. And let's see what we have if we do all that. Okay, so cleaning this up gives us the limit as x goes to infinity. So we said in the numerator we have so numerator square root. So this is the square root of x squared plus 1. And then downstairs we have x. So it seems like we're in this sort of infinite loop. This is problematic because we're not getting any closer to our solution. So you might say, well, L'Hopital's is broken, it doesn't work. Well, it works just fine because it says if you're in an appropriate form, then, for example, this limit is equal to this limit. It just turns out that's not particularly helpful. So then, of course, the question becomes, how do we break this loop? How do we free ourselves of the L'Hopital troll? So let's see here. Okay, so we're stuck in a loop. Okay, so here's where limit laws come to the rescue. So we want to carefully use limit laws. So let's try this again. So we're going to try and solve this without L'Hopital's because, well, I did get something true. Again, I didn't get anything particularly useful with L'Hopital's rule. So it's not a catch-all. It is important, of course, to know your limit laws. And so let's see here. So it's still in an infinity over infinity form. That's telling me that I want to consider doing some algebra, right? If I want to use limit laws, then I need to know that the limit of the numerator is some real number and the limit of the denominator is some real number. So to use limit laws, what I want to do is look for x to the highest power as x gets big. So as x gets big, this is really like the square root of x squared, which, since we're on the positive side, would be x. And as x gets big, this is x. So the highest power of x, or x to the highest power as x gets big, would be x to the first. That means I want to take this and multiply it by 1 over x to the first over itself. And the reason why we do that is we're hoping to get rid of the infinity over infinity and be just one step closer to being able to use limit laws. Okay, so I multiply by 1 over x over itself. So 1 over x to the highest power as x gets big over itself. Now, one thing I want to recall is the following. So let's recall a property of square roots, which is really a property of exponents, if you think about it, that if I want any hope of multiplying the insides, these have to have the same exponent, aka square root. So if I want any hope of multiplying this and this, both of these should be square roots, aka to the 1/2 power. These I can multiply just fine. That means I need a clever way to write this as a square root so these insides can, in a sense, interact. Well, here's where I'm going to start this because we're going to be just a little clever. So we're going to write this right here as the square root of 1 over x squared. I mean, as x gets big, this is still equal to this, right? I don't need any absolute values or anything. So yeah, as x gets big, this is just fine. This is equal to this. And that sort of solves our square root dilemma. And all over 1 over x. Okay, so this is quite nice because using this property right here, I can multiply this by this. So I'm going to distribute. So this will distribute here and here essentially. And these will multiply. So if x is big, I don't have to worry about either of these being 0, right? And so any number times its reciprocal will be 1. So I'm not too worried about that. So this is equal to the limit as x goes to infinity of the square root of, so this product right here, of course, this product will be 1. And then this product, of course, will be 1 over x squared. And as we mentioned before, this product is just 1, so I don't have to write over 1. And so this is actually pretty nice because our limit laws apply. Okay, so by our limit laws, this is equal to, so this is the square root of the limit as x goes to infinity, so I can move that inside. 1 plus 1 over x squared. And that's equal to, so I'm going to carry this through all the way with limit laws. So I can break the limit up over a sum. And now, of course, we can just compute. Okay, so computing this, we have to remember that the limit of any constant, no matter where you approach, is that constant. So this limit will be, of course, 1. And here, as x gets big, this denominator will get very large. And so the reciprocal of that will get closer and closer and closer to 0. And so this is the square root of 1, which, of course, is just 1. And so in that way, we have defeated the L'Hopital troll. How cool.